Hi guys, welcome to our channel of Sciences and Mathematics. Today we are going to do a topic in mechanics. Of course, it's going to be a quiz that we are going to try and solve, but specifically it's going to assist us to know how to find centripetal acceleration and then the centripetal force and also what we call the tangential speed that is experienced, of course, in circular motion. So in that case, we have discussed in one of our videos the concept of circular motion. And we are also going to borrow a few of the concepts that we learned from that video in order to assist us solve this kind of a problem. So for that case, thank you and welcome. So as I've said, we are going to do a quiz that I've written on the, of course, right side of the board. So in that case, this question is going to assist us to try and understand some of the concepts that we have learned in our previous video on the mechanics of course, an object that is moving in a circular motion. And this specifically, this kind of a question is going to assist us to solve a question regarding to tangential speed, centripetal acceleration, and of course centripetal force. So first we are going to start by trying to remind ourselves of a few concepts that we learned in our last video regarding the concept of motion in circular, or the concept of circular motion. So for that case, this is under the topic of mechanics, and specifically this is a circular motion. So in that case, we shall have just a small demonstration to remind us of what we had learned last time, so that it is going to be easier for us. So in that case, I've just drawn a circle and written 2 points, that is point A and B. And then I've got an angle that is prescribed at the center there, which is angle theta. And then for point A and B, that one denotes an object that is moving in this direction from point A to B along a circular path. So in that case, we can just have a look at the question so that we can see whether it is related to that. So it says an athlete swings a 6-kilogram ball horizontally in the end of a rope. The ball moves in a circle of radius 40 centimeters at an angular speed of 0.5 revolutions per second. Calculate Roman 1, the tangential speed of the ball. Roman 2, centripetal acceleration. Roman 3, maximum tangential speed the ball moves at 200 newtons. So of course that one is going to form a basis for our discussion for today. So as I've said, this one demonstrates the motion of an object in a circular motion. And then we said that the distance between A and B, or the length A and B, this one is the arc length, that of course has been denoted by the letter T, S. And then R represents the radius of that particular circular path. And then theta, this one implies the angular displacement of that object. And then O refers to the center. So in that case, when we are talking about velocity, we said that velocity is the rate of change of course that is a displacement over time. So in this case, if the object moves from A to B, this is the arc length, it will form our displacement, and if the time taken for it to reach point B is t seconds, then we give a representation of that particular expression as V is equals S over T. So this one gives us our expression for velocity. And then there's also what we have talked about, angular displacement. Now in this case, there's a relationship between angular, of course this arc length, and the radius that we have written. So we said that degrees can be measured, of course, in degrees, which is denoted as a small 0 there, or maybe in radians, which is denoted by small c or a superscript. Suppose I say that it is 2 degrees, then the other one will be 2 radians. So in this case, there's a relationship between the displacement AB and R, in a sense that when the degrees are measured, or angular displacement, of course, that we have given as theta, which is theta in radians. Now, angular displacement is usually given in radians, so when it is given as angular displacement in radians, which is theta, will be given as S over R. So that's the second equation, apart from the velocity that we have seen. So angular displacement is given as S, which is arc length over the radius. In the event that S is equals R, then we can say that that one represents what we call 1 radian. The displacement S over R, S is equals R, that is given as theta is given in 1 radians, which is 1 radian. Of course, if the displacement S is equals the circumference, which is given as 2 pi r, this will have taken, of course, that angular displacement. We know that a full circle has got 360 degrees. So therefore, if it's the displacement in degrees is 360 degrees, that is equivalent to the circumference. Now that one is referred to as a single revolution, which is given as 1 revolution. So 1 revolution is equivalent to 2 pi r, or 360 degrees. So therefore, we can say that, okay, just a minute. So if S over R, or the displacement is 360 degrees, which of course we say that theta is given as S over R, and then we've said that if theta is equals 360 degrees, this is equivalent to 2 pi r. Therefore, looking at the relationship between these two, then we can therefore say that 360 degrees is equals 2 pi radians. Therefore, a radian can be represented as 360 over 2 pi. So that's for a single, of course, radians. For us to, we can just do a simplification of this one by getting that this one is equivalent to 180 over pi. So this is for 1 radian. So from our equation that we have said, this is theta is equals S over R. Therefore, angular displacement S from this formula can be given as R theta. So having that one in mind, therefore for an object that is moving in a circular path, the speed can be described using two specific terms that we have of course mentioned. We have mentioned some of the terms that we have talked about, which is angular displacement, and of course this one. So I'm just going to just indicate that for an object that is moving in a circular path, of course now I can write this. I'm going to just explain what it means. An object moving from point A to B at a velocity, of course, first starting with a particular velocity, and then at point B to have attained a specific velocity. We use U to denote the initial velocity, where V represents the final velocity. Therefore, this speed along the circular path can be described by the speed along the tangents at an instant, like the one I've given for point A. This this point is described using the tangent at that point, and then the speed at point B, which is v, is described using that tangent v. So therefore we have two kinds of velocity for an object that is moving in a circular path. The first one is linear speed, and then the second one is angular speed that results due to angular displacement. So this one is given as or denoted as omega, while this one is denoted as v. So as we are going to use these particular terms, maybe necessarily in an alternating way, or maybe exchanging one for another, they specifically refer to as v as a linear speed, and then angular speed, or maybe we can refer to this one as a tangential speed, the one that we have of course described using the points A, B. So therefore we just look at this one. Now that we have been given a speed from that question in revolutions per second, of course the one for linear speed is measured in linear speed is measured in meters per second, and the angular speed, of course, I've talked about pi radians or revolutions per second. So in this case we are going to look at this relationship, which is going to assist us to solve the problem. So we can say that angular velocity will be given as angular displacement, which we said is theta. I'll just write the short form because of space. So it will be given as angular displacement all over the time taken. So this one is denoted as theta over t. So therefore, as we said that angular velocity can be represented by omega, we have another equation that is going to denote that, which is omega, which is angular velocity, is given as theta over t. But for angular or linear, tangential or linear speed is given as displacement over time. Of course, we say that the displacement is represented by s along this one. Of course, the described distance from A to B, or the arc length, is given as s over t. So if we try to look at the relationship, of course we had said that given s is equals r theta, therefore we can see that for velocity we can do a substitution for s for this one and say that velocity therefore is equals r theta over t. But from this point r theta over t, we have already given a representation for angular velocity, which is omega is equals theta over t, which of course is going to give us a substitution at that particular point. Therefore we can say that v is going to use this place. We can say that v is equals r theta over t, but given that r theta over t is omega, we can therefore write it as r omega. So for that case, the tangential speed at a particular point can be written using the formula v is equals r omega. So this is the concept that we are going to use, or the principle that we are going to use to solve our first question for Roman 1, bearing in mind that the other concepts that we have discussed, of course, we are going to also employ them in case there's need. So let's look at that and try to solve it for the first one. An athlete swings a 6 kilogram ball horizontally in the end of a rope. The ball moves in a circle of radius 40 centimeters at an angular speed of 0.5 revolutions per second. Calculate Roman 1, the tangential speed of the ball. So, Roman 1, this is the tangential speed that we are required to find. And we have been given some information, which is a radius 40 centimeters. Now we convert this one to a standard unit. This is 0.4 meters. And then we are given omega, which is an angular speed that we have denoted as omega is 0.5 revolutions per second. We said one revolution is equivalent to 360 degrees. Therefore, in this case, when we are finding omega, we can just, this is just a fraction of omega. So we're just going to calculate this omega in pi radians. And if we say that 2 pi radians represent 360 degrees, therefore in this case, a half a revolution will represent, so this is divided by 2. So I have a revolution, of course, for a circle, which is 360 degrees. I have a revolution will represent 180 degrees. So for us, 180 degrees in pi radians will represent a pi radian. So in that case, we're going to use that concept. So therefore, for us, omega will be equivalent to a pi radian. And therefore, given that we have said velocity is equals r omega, we have converted the radius to meters, so it will be 0.4 times pi. Of course, pi is a constant that we normally use, and this one is going to give us v meters per second, which is 1.257 meters per second. So that's the tangential speed of the ball at that particular point, given that information. And then we are going to look at centripetal acceleration, that is Roman 2. For that case, I hope we have understood that one. So we are going to look at the second concept of centripetal acceleration. Centripetal acceleration. Now for centripetal acceleration, we said that an object that is moving in a circular path, we still use our example that we had said, an object that is moving at a circular path at a constant speed, this is from the initial to the final speed, there's an aspect of acceleration that is realized due to the change in speed. As you can see, the speed is changing in direction. Changing direction of speed gives the concept of acceleration. And from our normal concept of motion, we know that acceleration is change. From kinetics, we know acceleration is change in velocity over time. But in this case, we have already said that velocity is given as r omega. And therefore, for linear acceleration, we talked about two concepts, that is linear and angular. So now for linear acceleration that we have given its concept there, acceleration is of course the derivative of velocity, given as that. Now for us, we will do a substitution for velocity from this concept that we have said therefore, and find that r omega over dt. So that's our differential. Still, of course, r is a constant which we have been given, so we shall have acceleration is equals rd omega over dt. Now in this case, the differential that we have written here for angular, of course that is an angular velocity over time. It's going to give us what we call omega. That's another, of course, term that we are going to use there. So for linear acceleration, which is denoted as AL, we will denote centripetal acceleration using C. For whenever I write L, this one represents linear acceleration. So in that case, we shall have our linear acceleration given as AL is equals R alpha. So now in this case, from Newton's second law of motion, I think we are going to borrow some specific concepts, bearing in mind that we already have a concept what they are. Newton's second law of motion states that force is a product of mass times acceleration. Now this one, I'm just going to give it that arrow indicating that it's a vector quantity. So in that case, force is a product mass times acceleration. And in this case, of course, we're going to talk about the concept of centripetal force. So if we are talking about centripetal force, then it is given as force equals mv squared over r. So implying that for centripetal acceleration, which is being experienced by our object that is moving in a circular motion, the mass for this object will just be the same as a constant. So for that case, the acceleration can be represented using that second part of the formula. So we shall have acceleration is equals v squared over r. So that's a representation for acceleration using that concept. Now for this case of an object that is moving in a circular direction, I said we denote AC as the centripetal acceleration. Now having said that v is equals r omega, therefore we can do a substitution for this formula since we have v squared and say centripetal acceleration is equals r omega squared. Just split it like this for simplicity. So r omega squared, and then we do cancellation for one r, which will give us omega squared r. So centripetal acceleration for us will be given as omega squared r, and that one is going to give us a basis for finding the second part of the equation, which is centripetal acceleration. So we shall use that one. So therefore, given that the radius, of course, is 0.4 meters, which is 40 centimeters, and then we have got omega, which of course was 0.5 revolutions, which is pi radians. So in this case, from the formula that we have written here, given centripetal acceleration is equals omega squared r, doing a substitution for this, we'll find that centripetal acceleration is equals pi squared times 0.4. So this one gives us pi. We do a substitution, of course, to four significant figures of that. This is for pi. We do a substitution for that and get that it is 947 meters per second. Of course, that one will be in four significant figures, assuming that other figures that there we've done them, of course, either rounding off to get that figure in four significant figures. So that's how we find centripetal acceleration for our Roman 2. Now for the last one, we're going to, of course, use also the concept that we have discussed about the centripetal force, which we have given as mv squared over r. The question says for us to calculate the maximum tangential speed, the ball moves at 200 newtons. So for that case, we said that centripetal force equals mv squared over r. Now given that we have the mass, we have got the force, which is 200 newtons, and then we've got the radius, then we can just do a direct substitution for this in order to find the required, of course, answer. So for that case, we have force as 200 newtons times the mass is 6 kgs times, of course, the meters I'm just going to do as assuming, of course, they are very much important because we have to ensure that they are in standard form, just like for the case of radius that we have indicated as 0.4, but we have to be keen in order to ensure that the meters or the units that we have put reflect what is required. So for that case, I have m, which is mass, v squared over the radius is 0.4. So in that case, we are going to make v squared the subject of the formula, and then find it is 200 times 0.4 divided by 6.0. So v is the root of 13.33. This is square, but of course So we're going to find an absolute value because velocity in this case is not going to be negative. And this one v will give us 3.65 meters per second. So that's how we're going to use the various concepts that we have discussed in circular motion in trying to solve the problems that we have indicated on the board. So first of all, what we have to be keen about is what we have been especially asked to find. And now that we have discussed various concepts and given the designation or notation that is relevant to them, which is applicable maybe for velocity v, omega for angular velocity, etc. That's how we're going to use the same concept in solving other problems of the kind. So in that case, guys, we're going to stop there for today. I hope that we have gotten one or two concepts from this. Now that maybe we come across others in other problem solving maybe times, we can be able to apply them. So thank you for today. Bye. God bless you.